So here we see our 5-1 example problems. The first problem reads, a 35 kilogram mass is raised to a height of 12 meters. How much gravitational potential energy, or GPE, does it have? So the first thing that we have to do is state our givens. As with any problem, knowing what we have to work with will help us figure out where we need to go with it. So the first thing that we have here is the mass. So we got that 35 kilogram mass. The next thing is that we're given the height of 12 meters. And so the question asks, how much gravitational potential energy does it have? So GPE is equal to mass times gravity times height. And we know gravity is always 10 meters per second squared. So putting this all together, the GPE is 35 kilograms times 10 meters per second squared times 12 meters. We just go to our calculator to multiply the three numbers together. And you get 4,200 joules of gravitational potential energy. Moving on to problem 2. A 45 Newton per meter spring is compressed by 0.25 meters. How much spring potential energy does it have? So once again, we look to our givens. Right here, 45 newtons per meter, that describes the spring constant, the value of K. That unit of newtons per meter is the spring constant unit, and it's compressed by 0.25 meters of distance. And so we just have to plug and chug. Our spring potential energy formula is 1/2. Let me fix that. There we go. Kx squared. 1/2 of 45 newtons per meter times 0.25 meters squared. Now make sure you do the square first. So 0.25 squared will give you 0.0625. So the 45 newtons per meter, that pretty much stays the same. This term becomes 0.0625 meters squared. And now we just multiply across. Don't drop your calculator. 0.5 times 45 times 0.0625 will give you 1.4 joules of energy. So for problem 3, we are looking at a 3,000 kilogram car traveling at 12 meters per second. And the question is, what is its kinetic energy? As always, state our givens. 3,000 kilograms, that is the mass of the car. 12 meters per second is its velocity. So we're just going to mark those down, 3,000 kilograms and a velocity of 12 meters per second. And that's all we need to get the kinetic energy. This is pretty much just a plug and chug. 1/2 of the mass times the velocity squared. And just like with the last problem, you want to make sure that you square the velocity, in this case velocity, first. So it's going to be 1/2 times 3,000 kilograms times 12 meters per second, which is squared. So 1/2 times that 3,000 will give you 1,500. That stays as kilograms, no change to the unit there. 12 meters per second squared is 144 meters squared per second squared. This gives us our unit of the joule, and so we just multiply these two terms together. 1,500 times 144 will give you 216,000 joules of energy. Quite a bit of energy there. So for these next problems, we're going to be given one of the energies and other quantities, and then we're going to have to figure out another piece of information. So in this one here, we are given the following question. A 4,000 joule box is 30 meters off the ground. What is its mass? So this is not uncommon, where we're given an unit of energy to describe an object. Knowing that it's in joules, that tells us that it's a form of energy. We have to figure out, based on the context of the question, what type of energy it is. It's off the ground, so that should tell you it's gravitational potential energy. And so that 30 meters has to be height. And so to get the mass, gravitational potential energy equals mgh. Divide both sides by gravity and height. So the mass is going to be equal to 4,000 joules divided by gravity. We're just going to use 10 to make the math a little bit easier here, by 30 meters. Pay attention to the order of operations in your calculator. You want to do 4,000 divided by, open parentheses, 10 times 30, close parentheses, and we will get that the mass of this object is 13.3 kilograms. So continuing on here, we're taking a look now at problem 5. Now this one's a little bit more straightforward. Find the velocity of a 20 kilogram box if it has 3,500 joules of kinetic energy. So this problem is very explicit with what it gives us. We know that we've got a 20 kilogram box that has 3,500 joules of kinetic energy. We're tasked with finding the velocity. So we know the mass is 20 kilograms. There's really no question about which form of energy we have. That's explicitly stated for us as being 3,500 joules of kinetic energy. Now, the challenge in this problem is actually more in solving out the equation for the velocity. This equation's a little bit more complicated to rearrange. In order to get velocity by itself, start by multiplying both sides by 2. That's going to get rid of the 1/2. Then divide both sides by the mass. That gets rid of the mass on the right-hand side. This leaves us with velocity squared equals twice the kinetic energy divided by the mass. And now to get rid of that square, we have to take the square root of both sides. So our equation becomes velocity equals the square root of twice the kinetic energy divided by the mass. And so now that we've rearranged it, we can plug and chug. 2 times 3,500 divided by 20, and then don't forget to take the square root of that answer, will leave us with 18.7 meters per second. Now we're just going to leave this as positive. We don't know anything about the direction the object is going, so we'll just leave it as a positive. If we were indicated that there was multiple directions involved, we would have to consider whether it's positive or negative. So problem 6, probably the most difficult problem that we're going to take a look at here. Find the spring constant if a spring is stretched by 10 centimeters and stores 560 joules of spring potential energy. Now, the given information is pretty straightforward. The spring is stretched 10 centimeters, storing 560 joules of spring potential energy. X is 10 centimeters. The SPE is 560 joules. We're looking for K. However, the units are not correct. We have to convert 10 centimeters into meters. So we move the decimal 2 places to the left, and now we can solve out for K. Spring potential energy is 1/2 kx squared. So to get rid of the half, we multiply both sides by 2 and divide both sides by x squared to get rid of that on the right-hand side. There is no need to take a square root in this problem. We are not solving for x. We're solving for K, and K does not have a square on it. So K is twice the spring potential energy divided by x squared. So we have 2 times 560 joules divided by 0.1 meters squared. So the first thing that you have to do is that square. 0.1 squared will give you 0.01. And then multiply 2 times 560. That'll give you 1,120 up top. 1,120 joules up top divided by 0.01 meters squared in the denominator. And dividing those two, 1120 divided by 0.01 will give us a really large spring constant, 112,000 newtons per meter. And that's the answer to number 6.